Control systems seem complex only until you realize that stability and correction are part of everyday life. Welcome to the Learning Studio, where we don't just teach subjects. We break them down to their core intuition so you understand why systems behave the way they do, not just how equations are solved. Most students think control systems, including PID controllers, stability analysis, and root locus, are abstract mathematical tools used only in advanced engineering, but in reality, they exist to solve one simple problem: how to keep systems behaving the way we want despite disturbances and uncertainty. Whether it's maintaining speed, position, temperature, or balance, control systems are everywhere. To see this intuitively, think about driving a car. If the car goes too fast, you ease off the accelerator. If it slows down, you press it slightly. Your steering constantly corrects direction based on where the car is and where you want it to be. This continuous adjustment is exactly what a control system does. A PID controller formalizes this behavior by reacting to present error, accumulated past error, and predicted future trends to keep a system stable and responsive. At a deeper level, stability determines whether a system settles to a desired state or spirals out of control. Root locus and other analysis tools help engineers visualize how system behavior changes as parameters vary, allowing them to design controllers that respond smoothly without oscillation or instability. Instead of trial and error, control theory provides a structured way to predict system behavior before implementation. On a larger scale, control systems are essential in aircraft autopilots, industrial automation, robotics, power systems, and even biological processes modeled in engineering. From maintaining grid frequency to balancing robots and stabilizing drones, control theory ensures precision, safety, and reliability across complex systems. In real engineering practice, control systems are applied when tuning PID controllers, designing feedback loops, improving system performance, and ensuring robustness under changing conditions. These principles were developed and refined by engineers and mathematicians to create predictable and scalable systems that can operate autonomously. Now that the intuition behind control systems is clear, the next step is to explore state space analysis and modern control techniques, where control becomes more powerful and adaptable. And that's exactly what we'll cover next here at the Learning Studio.